through it. Well, I think I have to speak through it. But in the problem that I gave you for Stokes there, we could flip the sheet, the stock example. The curve is different. It's still a triangle, but my X, Y, Z I slightly have different. Like so. I still have the same triangle. My C is the first triangle that I drew up. And I'm going to apply Stokes' theorem. And I'm going to do it step by step. And there are reasons why these all hold. The theorem actually is proved in your book. At least an engineering proof is in the book. It's not a mathematically like sound version that would pass a math graduate class, but it's good enough. So the concept is the following, that the curl, which is on the little concept quiz I'm giving you today, the curl measures the intensity of rotation. So if you have a force in 3 dimensions, there's 3 different directions now that the wind could be blowing, right? So you can kind of think of like that force. I use a paddle wheel to kind of understand it. If you have a paddle wheel like this, and it has paddles, typically you have water as a force to move and rotate this thing around. What if the force that's being applied to each one of these paddles was exactly equal? What will happen to that paddle wheel? Stays the same. It doesn't move. So then the curl would be 0 in that case because the intensity of rotations was 0. So if the F was constant at every single point in X, Y, Z space, then this thing's not going to rotate. Does that make sense? Have you ever like held up a windmill? That's kind of like the same thing. If sometimes a windmill won't move at all because the force that's going on it is just, it's like canceling everything out. And like here, if there's water pushing, it's going to rotate. But here, if it was the same force, it's going to resist it and it's going to stop it from moving and turning. The curl is a measurement of the intensity of that rotation. If I spit out only water at the top, it's going to rotate. But the force that's hitting here is not going to be the same as the force that's hitting here because the water's right up here. So when this force goes through, it's not going to be exactly the same. That's why this force is going to be a function of X, Y, and Z. It's going to be the position that matters. And the steps, I'm just going to go through the steps, and you can ask me questions as I move along. So if I want to apply Stokes' theorem, the formula looks like this, which is kind of useless because it doesn't tell you, it's not a how to. Like this, we write it like that. But here's how to execute it. Step 1 is to compute the curl. So I got this F, I'm going to write it as P, Q, and R. In your book, for Green's theorem, they only had a P and a Q. Now you have an R. The P in our case is minus Y. The Q is X, and the R is 0. And believe me, I was trying to make it easy on myself. The formula for the curl looks like this, and this should go on your formula sheet. Again, efficiency is huge for you guys. When you have a formula, just put it on the sheet right away, or at least take a list so you're not starting from scratch. So this is why I have my glasses on. I couldn't see the subscripts. That's the formula for the curl. I'm going to skip taking all these partials by hand. But the point is, you won't be asked find the partial derivative on your T. They can just ask you this, find the curl. 2 birds with 1 stone. right? You have to find the partial derivatives as you go anyways. So it turns out when all is said and done, you can check my math. This thing is going to be 0, 0, 2. Let's just double check this one, just so you can see what is qx. What's the derivative of q with respect to x?
1.
1. What's the derivative of r with respect to y? P with respect to y, sorry. Negative 1. 1 minus the minus 1 is 2. So you see where those are coming from. So I'm just plugging and chugging. I assume everybody in here can take partial derivatives at this point. So, and then step 2 is to choose a surface. You remember that example I started out with that you're blowing bubbles? Maybe we should blow bubbles. Yeah. So you blow a bubble and you have the rim around it. The easiest one, the shape that you have, is when it's flat before you start to blow. As you start to blow, the surface that comes out of it is going to be some kind of paraboloid. So it gets more complex. What Stokes' theorem says is the surface doesn't matter. You can choose the easiest one possible. In this case, I could have like weird things. I could have the triangle coming out with a cone out of it. I could do weird stuff with it. But the easiest thing I could possibly do is to just make it flat, a triangle. The triangle it started out with. So that's what it means, choose the surface. I choose the triangle. The vertices were given to me. Okay, next step is to parameterize this. That's what your homework is tonight. Step 3, parameterize the surface. I feel like you did this before I got here. Remember the stuff with the U's and V's? You guys have something with U's and V's?
Differentiation by parts.
You guys do parameterization of a plane? Does that sound familiar? With a little U, V? Okay. You just thought, I think you did something with a U and a V. But if not, I'll break it down. You have 3 points on this line. You have 0, you have 1, 0, 0. You have 1, 0, 1, 0. And then you have 0, 0, 1. Those are the vertices. You have two direction vectors. You first form the direction vector with these two guys, and so your formula looks like this. It's going to look like P0, still the start point, U times direction vector 1. I don't know what they called it in your notes. And then V, wait, let me do it this way. Yeah, this is how they should have written it this way, I think. So you have two direction vectors to compute. Kind of ringing a bell? I think you did it. It doesn't matter. So your V1 is going to be tail to head from the first 2 points. So you're going to do tail to head. So it's going to be -1, 1, and 0. And your second one is going to go through the second 2 points. So it's going to be, this is going to be your start and this is going to be your end on the triangle, which is drawn really nicely up here. So what's going on is your top point up there at 0, 0, 2, and in my case it's 0, 0, 1 would be the start, and the end point would be 1, 0, 0. So your V2 is going to be start at 0, 0, 1, end at 1, 0, 0. You get minus 1, 0, 1. That last line segment. So your parameterization is going to look like this. That's what it's going to look like. It's this whole thing. It's not RT, it's RUV, sorry. There's 2 letters. Because you're on a surface now. That's what your homework is tonight. You're going to be doing this.
Doesn't matter what you select for your teleheads.
Which one?
Doesn't matter what you select for your telehead for V1 and V2.
Yes, it does. Because they have to tell you the direction of the orientation. Because there is a orientation for this curve counterclockwise to make Stokes work. It's just like Green's is a special case, so you have to go counterclockwise. So the orientation matters. So since we're going counterclockwise, my first start point is 1, 0, 0. My second one is 0, 1, 0. My third one goes from 0, 0, 1 down to 1, 0, 0. Make sense?
Wait, you can only do this with commands, right?
This only works for this case, right? So I think on your homework you have a plane, and then you have a cylinder thing. You have 2 planes and then a cylinder thing. I matched them pretty well, and I explained it really well, like what's going on. I think I did. I won't know until you tell me. So maybe I didn't. But I put a lot of detail on how I came up with the parameterization. There's really only 2 things you can do. You can only work with lines, planes, or something that's circular, because then you can use polar coordinates. Do you kind of recognize that from your WPR 5? You only had a few possible choices that we could give you that was really easy enough to do on a WPR. You know how to parameterize a circle. Cosine t, sine t. That showed up. You know how to parameterize a line. That showed up. You know how to parameterize a plane. That's probably going to show up. You know how to parameterize a cylinder with cylindrical coordinates. That's probably going to show up. All right, I am going to pause there. The rest of this, I'm going to work out. I can either do 2 things. How is it more accessible to you? I can make a video that finishes this problem, or I can toss lecture notes into the same place that the board sheet is, so you can see these worked out.
Second option.
Second option?